Hi, welcome to this training segment with Enphase Energy. I'm Peter Lum with Enphase Learning and Development, and this session is on understanding integrated ground microinverters from Enphase. This training session is to help our students gain a deeper technical understanding of the integrated ground technologies used in Enphase's IG, or integrated ground equipped microinverters. In this segment, we will review system grounding requirements and want students to be able to explain the difference between a DC system ground, or DC GEC, and a system equipment ground, or EGC. We also want students to be able to explain the difference between an Enphase microinverter equipped with an integrated ground and one that is not. And finally, students should also be able to describe some of the safety benefits of having an integrated ground technology. So let's get started. First of all, from a safety perspective, we should remember that grounding and ground fault protection continue to be critical areas of concern in the design and installation of PV systems. Shock hazards associated with power systems are of concern for system owners, installers, maintenance personnel, and emergency workers, and concerns about PV systems causing fires are also rising. In our session today, we will discuss how integrated grounding technology addresses industry concerns and offers enhanced safety. Enphase Energy is now offering integrated ground microinverters into the industry. These are PV solar inverters with DC electronics which are electrically isolated from the inverter enclosure. Because of this isolation, the inverter does not require a DC system ground or DC GEC grounding electrode conductor. This is typically the number 6 or number 8 continuously run unbroken wire installed onto each inverter by installers, or the grounding washers installed by each installer were improved to bond the inverter to the racking system for the DC system ground. We'll discuss the architecture in depth later, but IG-equipped microinverters eliminate the need for the DC GEC wire or grounding washer. The IG inverters offer greater safety because of DC isolation and greater system simplicity without the need for the ground wire. With an integrated ground microinverter, installers are now able to use this technology to build safer ungrounded systems. Now, Section 690.35 of the National Electrical Code does allow for the building of ungrounded PV systems when a number of conditions are met. These conditions are intended to make ungrounded PV installations in the United States as safe as equivalent ungrounded PV systems in Europe. So the National Electrical Code requirements were developed to bring the U.S. PV industry in line with the rest of the world by adopting some of the European techniques and experience for installing ungrounded systems. On the page displayed is an excerpt from the NEC outlining the code for ungrounded PV power systems. We won't discuss this in detail, but we'll refer to these requirements when we discuss integrated grounding in Enphase's microinverters. As previously mentioned, with an integrated ground, we're no longer in need of a DC system ground, or DC GEC. When eliminating this ground, it's oftentimes mistakenly understood that we are removing all grounding from the PV system, and this is not the case. To clarify this, we should briefly review the grounding for a PV system. There are two basic types of ground that are usually associated with a PV system installation. The first is the ground requirement for the electrical system. Electrical components that normally pass power and are part of an electrical system need to have a ground path in the event there's an electrical fault. For solar inverters, there are two associated power systems, the AC power system and the DC power system, both contained within the inverter. Because the inverter circuit is connected to the AC of the building, the AC side of the PV system already has an AC system ground or an AC GEC grounding electroconductor via the grounding system of the house. The DC power system, however, within the solar inverter also needs a ground. Everything associated with the DC power system needs to be grounded so that if there is some sort of DC electrical fault, there would be a ground path for the DC electricity for safety. To provide this DC system ground, a DC grounding electrode conductor or GEC wire is installed. Now the requirements for this, based on the National Electrical Code, are typically a minimum wire size of number 6 or number 8 copper wire run to each device that requires the DC system ground. The wire has to be run continuously, and if broken, are bonded back together with an irreversible means. Again, this would be a DC GEC. So that is a system ground. That's the first requirement for a PV system installation. There's a second type of ground associated with a PV system installation, and that is the equipment ground. An equipment ground is intended for metal pieces used in the environment which are not associated with any power system, but because metal is conductive and could get charged with energy, if a fault occurs, the metal needs to have a ground. And so this is typically referred to as an EGC, an equipment grounding conductor. That's a wire for metal pieces. And this would typically be for the aluminum racking of a solar installation, the metal frames of solar modules, the metal enclosures of inverter devices, junction boxes, and so forth. Metal pieces that typically are not associated with any kind of power system usually needs an equipment ground through an equipment grounding conductor. Both of the grounds that we mentioned are important. Both the system ground, the GEC, or the equipment grounding conductor, are both important, and even though they are ultimately both bonded to ground, have different requirements which must be met to be code compliant. For Enphase integrated ground equipped microinverters, the integrated grounding removes the need for the DC system ground, or DC GEC, but not the equipment ground, EGC. You still need that. So to understand this a little better, let's take a closer look at Enphase's integrated grounding. To understand integrated grounding, let's first take a look at a traditional grounded inverter architecture to understand how grounding works and why it's required. Recall that one of the requirements that must be met by any solar inverter is that there needs to be provision for DC ground fault protection. So solar inverters in the United States are required to both detect a ground fault and to shut off the circuit if one is detected. So the typical method, which is commonly employed, is to bond one of the conductors of the circuit to ground so that there is a ground reference. Pictured here is a diagram of the architecture of a non-integrated ground Enphase microinverter. As with most solar inverters, the way that a ground fault is detected is by using a GFDI circuit. GFDI simply means ground fault detection and interrupt. In the architecture, the GFDI circuit is tied in line to one of the DC conductors of the DC circuit and then bonded to ground so that there is a ground reference. Remember, if we want to detect a fault to ground, we also need a reference to ground. The ground connection is usually the metal case or inverter enclosure. So here's the important thing to recognize. Because we bond one of our DC current carrying conductors to ground for our GFDI circuit, in this case the enclosure of the inverter, the metal case of the inverter has now become a part of the inverter's DC power system. As we mentioned earlier, a power system is required to have a system ground. In the inverter, the DC power system is required to have a DC system ground, or DC GEC grounding electroconductor. Since the case of the inverter is now associated with the DC power system, we need a system ground which touches the case of the inverter. To provide the DC system ground, installers typically run a number 6 or number 8 wire connected to the case of each inverter. Or in jurisdictions where permitted, grounding washers are installed to bond the case of the inverter to the racking system to provide a ground path. On Enphase microinverters without integrated ground, the ground requirement is shown by a stamped ground symbol on the metal flange of the inverter, indicating that the case requires a ground connection. And there's also a ground lug on the flange of the inverter so that the GEC wire can be attached. Taking a look back at our diagram, you should notice that there's also a second grounding point. This is an internally bonded ground connection between the inverter to the output cable of the inverter and connected to the main trunk or bus wire. Since there appears to be a ground connection to the trunk or bus wire, people have asked about using this ground wire in the main cable for our DC system ground. The simple answer is that the wire sizes in the main cable are not sized to be a GEC. The internal wire would be adequate for an equipment ground or EGC, but not for a DC system ground. So the number 6 or number 8 wire still needs to be run through the grounding lug on the flange of each inverter. So in quick summary, because there is a ground connection from the DC power system to the case of the inverter, the case of the inverter is now considered part of the DC power system and requires a system ground. So let's take a look how integrated grounding changes this picture. Enphase integrated ground equipped microinverters have a totally isolated and insulated DC power system. The DC to AC power system is isolated through a transformer, and there's a newly implemented method for ground fault protection which doesn't require a direct bond or reference to ground. Enphase's new ground fault detection and interrupt circuit is based on an insulation monitor technology. The insulation monitor, or IM, measures insulation resistance in the wiring of the circuit. How does it work? Wire insulations should have normally a very high resistance value, as insulators should not allow current to pass through the insulator. Wiring that's compromised, on the other hand, exhibits a low resistance path to the outside of the insulator. An insulation monitor is able to detect low resistance paths in the circuit through monitoring resistance values. If a ground fault should occur, in other words, if a conductor, positive or negative, should fault and short to ground, the IM would indicate this as a resistance problem and signify a fault. With the insulation monitor method, a ground fault is detected without the need to reference ground directly. Without the bond to ground, as in grounded inverters, there's no association of the case of the inverter to any of the DC power system. Since the case is isolated from the DC electronics and the case is no longer considered part of the DC power system, there's no longer a need for a DC system ground or a DC GEC grounding electrode wire. So no more number 6 or number 8 wire. The flange of the inverter no longer shows a grounding symbol, and there's no ground mounting point for a ground wire. Because the housing of the inverter is still metal, there's still a requirement for an equipment ground, or EGC, to the inverter. As noted before, there is an internal ground point within the inverter to the case of the inverter. The bond point is wired to the internal wiring of the output cable of the inverter and eventually connected to the main bus wire. To provide a EGC, installers can simply connect the ground wire of the main cable and wire that to the main grounding point in the electrical panel. The bottom line is that no external copper wiring is needed with integrated ground-equipped Enphase microinverters, and equipment grounding is available through the internal wire in the wiring harness. Okay, it's time to do a little learning check and see if you're picking up these things that we've been telling you. So we've got some questions for you. The first question is, why is the GEC not required when using an integrated ground or IG equipped Enphase microinverter? Is it choice A, because the integrated ground microinverters are lower powered and so there's no danger of DC problems? Or is it option B, the equipment grounding conductor or the EGC takes care of all of the system grounding needs? Or is it C, the integrated grounding isolates the DC ground, so we don't need DC ground? Or is it D, the grounding washer is usually used instead? So the answer is, of course, C. The integrated grounding isolates the DC ground from the case of the inverter, so there's no longer a need for the ground wire. Here's the second question. Do integrated ground microinverters still require an equipment ground or an EGC? And the answer there is yes, absolutely. The integrated ground microinverters still have metal enclosures, and because those are metal enclosures, they still require a equipment ground. Next question, when installing an integrated ground microinverter, how do you provide the equipment ground or EGC? Is it A, you run a separate wire to each inverter case, or B, use a grounding washer between the microinverters and the railing, or C, you really don't need an equipment ground, or D, it's built in to the engaged cable or the main bus wire? The answer, it's D. It is built into the internal wiring of the harness, and so the equipment grounding can be found there. Additional resources can be found at enphase.com. If you go to the resource section and under Download Library, you'll find a wealth of information regarding Enphase. Specifically for integrated grounding, we do have a one-page technical brief and a 4-page white paper which talks about integrated grounding in depth. Thanks for joining us on this learning segment. We look forward to catching you on our next one.